Já estamos ao vivo, pode dar início, tá, Mark?
Desculpe, posso começar ou não? Não
Isso,
entendi.
pode ser.
Ok, começo então. Ok, boa tarde a todos. Estamos aqui para fazer a defesa de mestrado do meu estudante do CPPF, o Alexandre Sampaio da Cruz. Ahm, temos dois examinadores, um deles externo da Irlanda, então vamos prosseguir em inglês. So we're here for the presentation for the defense of my student, Alexandre Sampaio da Cruz. He's going to give a presentation for about up to 50 minutes. The external examiners are Barry Wardell from University College Dublin, Ireland, and Sergio Giras from UFRJ. So after the presentation, then they'll be able to ask questions. You can ask questions during the presentation, but it's preferred to wait until the end. Okay, so as far as I'm concerned, I think we can start. So Alexandre, whenever you wish, you can start your presentation.
Okay, so good afternoon, everyone. I'll be holding now my thesis defense for the obtention of the title of Masters in Physics from CBPF. I would like first to thank everyone that is present today, the examining board, also everyone that is present on YouTube, and also my advisor. So I decided to divide this presentation into 5 sections as opposed to the 7 chapters that I have in my thesis. So for the first part, I'll just talk about an introduction, and first of all, the motivation for the things that I have studied in my master's. So two-body problems in general relativity, they get much more complex than their classical physics counterparts. The most famous classical physics two-body problem being the Kepler problem. And in general relativity, 2 distinct features of the gravitational two-body problem arise. First of them is that a system of 2 bodies in general relativity would typically emit gravitational waves, which carry profound astronomical interest. And also there's the fact that the equations that govern this type of systems are much more complex than their classical physics counterpart, meaning that we'll usually need to we'll usually not be able to solve them in analytical closed form for the dynamics of the system, but there are many tools that we can use at our disposal for tackling the study of this type of system. Here I repeated the same image that I have in my thesis, which I took from Wikipedia, which displays the 3 main different methods for studying the two-body problem in general relativity, and their specific the domain of the parameters, such as the separation between the bodies and the mass ratio in which that they excel. The most straightforward one would be numerical relativity. Just plug the equations into a computer and solve them numerically for some initial conditions, which may or may not be computationally expensive, depending on the kind of system that you're dealing with. Then we have the analytical methods, which are both perturbative methods. The first one being post-Newtonian theory, which are basically expanding the equations about Newtonian physics, with your 0th order solution being for the metric being the with your 0th order description of the problem being the one by Newtonian physics. And we have black hole perturbation theory, in which we're expanding the physics of the system about a black hole solution in general relativity, such as Schwarzschild or Kerr solution. We're dealing with this regime, and this regime is of particular interest right now due to the upcoming LISA experiment, which will be a space-bound gravitational wave detector experiment that will detect for which one particular source that it will detect are the extreme mass ratio in spirals, which are binary systems comprised of 2 bodies, with one being much more massive than the other one. So the basic picture of black hole perturbation theory is that you take the the metric of that of the space-time around your binary system to be given by zeroth order solution at zeroth order by the metric of the more massive black hole. The zeroth order metric would be a Schwarzschild metric or Kerr metric. And you consider, here we're talking about linear perturbation. So we consider a first order perturbation due to the presence of the least massive body. So at zeroth order, in this perturbation theory, the small body is seen as a test particle, so it follows a geodesic of that background geometry. And if one goes to first order in the perturbation, what happens is that this body will actually deviate from this geodesic motion. And from the perspective of the background spacetime, this deviation is seen as a force due to the perturbation field, the perturbation linearized gravity field h mu nu, whose source is the mass itself. When solving for this perturbation, solving the linearized gravity equations for this perturbation, we can treat it as we can treat the particle as a point source, meaning that so since we are interested in calculating the effect of this point source perturbation at the position of the particle that sources it itself, we're dealing with a self-force problem. Then we need to introduce some methods, some regularization methods, in order to cure this problem from its very intrinsic singular nature. As it turns out, this type of problem is actually belongs to a broader class of problems of calculating self-forces on generic charges on curved spacetime. So you can have an analogous problem with the electric charge or with the scalar charge. And the main aspects of the regularization procedures that need to be introduced, they are not dependent, do not depend a lot on the nature of the field, on the spin of the field. One can focus on the study of the scalar charge first and develop methods in this context in order to later regularize generalize them for the more interesting gravitational case. So for the rest of this work, I'll be talking only about scalar self-force. I'm not talking about gravitational anymore. So here I go very quickly about the basics of the dynamics of the system. So you have a scalar charge Q that travels along a geodesic, which I labeled gamma, and the field generated by this charge is going to be a solution to the Klein-Gordon equation, which can be obtained, which can be described in terms of Green's function. So we seek Green's functions to the Klein-Gordon equation. And then the retarded, and we define retarded and advanced Green's function to the Klein-Gordon equation as possessing so a retarded Green's function is defined as possessing the property of vanishing for a field point x. A retarded Green's function is defined to vanish everywhere else except for the past light cone of the vanish everywhere else outside the past light cone of the field point x, while the advanced Green's function is defined to vanish outside the causal future of the point x. An important distinction between flat and curved spacetime is while in flat spacetime, this Green's function, the retarded and Green's function would contain only support on that cone, on those cones, on the surface of those cones. In curved spacetime, due to the fact that waves may propagate with velocities that are less than c, we have the fact that the support of this Green's function must also include the insides of those cones. So, for example, if you look at the retarded Green's function here, in flat spacetime, you would have that the field at the point x depends on information at the retarded point, and in curved spacetime, it depends on every other point that is before on the borderline of that retarded point. So now I give some definitions for some formal definitions that for the quantities that we'll discuss. So I would denote the self field with the as being the limit as the field point x goes to z of the field. So if I calculate the field at a point x and take the limit as x goes to z, with z being any point on the world line. And also, so similar for the full self force, we define it as the limit of the gradient of that field. And we also include this projected tensor here, so just so that this definition preserves the norm of the forward velocity. And we can also express the bare self force in terms of the Green's function, by expressing the field in terms of the Green's function. I will use the convention everywhere else to be evaluating the self force at tau equals 0. We can just evaluate for any point on the world line. And all of these are just formal definitions because we have not talked about regularization yet. So they are just valid on a formal level. And okay, so I will now briefly talk about the Tweiler-Whiting regularization scheme that can be used to define a regularized field, regularized self field. So basically, we define a regularized field as being phi, which is the bare field, the retard due to the retarded using the retarded Green's function, minus a field phi s, which is defined to have the following properties. It must be just as singular as the retarded field, so that this subtraction here yields a regular term. Mathematically, that means that it must be a solution to the same Klein-Gordon equation with the direct functional source, with the point source. And also, this field must be associated with no physical self force, since we do not want its subtraction to actually alter the physics of the problem. So it can be shown, this field can be shown to be given by this particular choice of Green's function, to be obtained from this particular choice of Green's function, which contains half the advanced and half the retarded Green's function, plus another term here that is introduced only so that this definition will be causal. And a particular property that this singular field carries is the fact that its Green function is only support on a small piece here of the world line, and we can see that as we take when we take the limit where the field point x goes to the world line, this field will be actually supported. It will be sourced only at the position x itself, meaning that it can be written in terms only of local quantities, as opposed to the regular field, which contains the retarded field, which has support on the entire past history of the particle. Okay, now I introduced the mode sum method, which would be a scheme that we'll use to perform this subtraction, to perform this regularization. So by now I'll be specializing the discussion to Schwarzschild spacetime from now on. So in the mode scheme method, we perform the subtraction we perform this regularization of the field by obtaining the L modes of the retarded field and the L modes of the singular field, and subtracting them before doing the summation over L. This L modes of the field, they have the property of being finite even at the self field limit, so that the singular nature of the retarded and singular fields it only appears as the divergency of the L sum. So if we perform the subtraction before, the L sum would then be guaranteed to converge, and we can do that either at the level of the field or at the level of by defining a regularized self force at the level of the self force. Okay, so since the field, the singular field, can be expressed in terms of the local quantities, as I said, one can the general form for it is known of its L modes. It looks like this, where A, B, and D are called the regularization parameters, and is the presence of the A carrying term and the B term that makes the sum of this over L diverge. And later on, we'll be deriving this expressions for these quantities for the circular geodesic. And then to obtain the modes of the self force, of the bare self force, we're going to perform a decomposition of the field into Fourier harmonics. So we're also decomposing its time dependency. And by doing that, our radial modes of the fields, they are solution to a specialization of the Minkowski equation, which is an equation for general perturbations in Kerr. But here I have it specialized to Schwarzschild. It carries a spin weight factor, so it different values of S give the perturbation different spin perturbations. We're interested in the S equals 0 case of this equation, but I introduced it in general form since I will be using some methods that were developed for general spin, and there's no reason to specialize at this point. So to construct the solution to this source equation, we will look for homogeneous solutions that from which we can construct the Green's function that has the properties of waves that are generated by localized charge, meaning that the waves are ingoing at the horizon and purely outgoing at infinity. So here I define the property. These are the solutions having these properties, purely outgoing at infinity, and purely ingoing to horizon, and purely outgoing at infinity, where we express everything in terms of this tortoise coordinate, which has the effect of actually placing their horizon, which is r equals 2m at r star equals minus infinity. Okay. The solutions to the Minkowski radial equation are related to the solutions to the Regge-Wheeler equation. And in the particular case of the scalar charge, transformation between the two solutions to the two equations is trivial. So the Regge-Wheeler equation is another perturbation equation valid only for Schwarzschild. And their transformation in Kerr is just a division for the scalar charge, just a division by r. And the solutions to this equation, they behave like regular waves. They have this asymptotic behavior at infinity at the horizon, just like purely outgoing waves, with no additional r prefactor here. And then once we obtain this in and up solution, we can construct for the radial equations, we can construct the 4D retarded Green's function by considering here the angular part as well. Okay, so right now I will discuss, we work with the Regge-Wheeler equation, and we'll apply the WKB method to obtain large L solutions for it that will be later used to construct the expressions for the regularization parameter. And this is not like the usual way to obtain these parameters. One usually obtains them from those local expansions of the quantities as I mentioned before. So we take this ansatz for the Regge-Wheeler radial function, and by applying that ansatz to the Regge-Wheeler equation, one arrives at this solutions for the first few S functions here in the series. This is exponential series. This series terms appear at the exponent. The important thing to highlight here is that all of the even functions, they carry plus or minus signs, while the odd functions do not. And this will define two independent solutions. One independent solution will be by taking all positive signs, and another independent solution will be by taking all negative signs. And another thing that is important to see is that all of these contain half integral powers of u, or maybe whole powers of u, whole inverse powers of u here in the denominator. And so if we have u equals 0, we're going to have a problem with this solution, which corresponds to the turning points of the equation where the WKB method becomes invalid. So in order for this series to be convergent, usual requirement for convergence, we require that every next S function should be much smaller than the previous one. And this, of course, will not hold for u equals 0. And then we check the behavior of the S functions as L goes to infinity. And as long as this particular condition here is met, which corresponds to u being greater than 0, this S functions, the WKB solutions actually, they resemble a generalized asymptotic series in L. So we can construct large L solutions based on that. So but we actually want to construct solutions that satisfy those in and up boundary conditions to construct the Green's function modes. Turns out that this when you go to R to the horizon and R to infinity, RSV here being the event horizon, you have the fact that the potential V goes to 0. So at some point you're going to have U equals 0. We call that U is omega square minus V. So that we cannot bring the WKB solutions obtaining this positive U region all the way to the horizon and all the way to infinity. So we cannot enforce boundary conditions directly on them. We must instead match them with solutions, with asymptotic solutions that already have this in and up properties. So now we're going to actually derive some asymptotic solutions that already have this that we're going to enforce on this asymptotic solution, the in and up boundary conditions, so we can match them with a WKB. So to derive an in solution, a leading order asymptotic solution, we can construct a leading order asymptotic solution near the horizon by expanding the potential for a small displacement delta R away from the horizon, and so near the horizon, we can find an approximate for the Regge-Wheeler equation near the horizon to leading order in delta R, which is the displacement from the horizon. And we arrive at a solution in terms of a combination of modified Bessel functions. Then we can enforce in boundary conditions onto this solution, and we arrive we obtain an expression for the in solution, which is given by only taking only the negative order Bessel function here. Okay, so we need to match this solution with the WKB solution, and to do that, we take this asymptotic in solution and expand it into the direction where the WKB is valid. I think I got. Okay, I don't know why this slide it got. I think I double passed. But so here I have defined the two so here I just redefined the S functions so that the plus solution is given by the choice of all of those plus S functions, and the minus another independent solution, WKB solution, WKB minus, is given by choosing all of these minus functions that I said that make up the two independent WKB solutions. We can take a leading order approximation to this expression, and then by doing that, we need to consider the two first S functions here, and we arrive at these expressions, and it is these leading order expressions that we're going to actually use to match with the in and up asymptotic solution. So going back to the in solution, here we find out that the leading order WKB solution can be matched to this solution by realizing that the so this comes from the WKB plus part. It contains exactly the same exponent here as this term, while the minus part of the WKB solution is matched to this latter term here. So the WKB leading order in the WKB expansion solution that is matched to the asymptotic in solution looks like this. However, we can further simplify this by noticing that the function, because we want to take the L of, at the end, we're going to take the L of, to infinity of this. And this WKB minus solution, it contains exponential of minus, it is led by exponential of minus S0. And S0, as I showed before, is of order L, and is also a monotonically increasing function with L. So when we take the L of the infinity limit of this WKB in solution, this function decays exponentially with L. So its contribution to the general WKB in solution will fall faster than any higher order term that we can include in the plus solution. So we can just get rid of the minus part and just consider the plus part as L goes to infinity. then we express our WKB in solution. It is exactly like equal to up to a normalization equal to the WKB plus independent solution. We do the same thing to obtain an up solution. I will go faster through this one, except that we expand for large radius, and then we obtain a solution to an approximate to an asymptotic equation near the horizon, far from the horizon, that satisfies the up boundary condition for the outgoing, and it can be expressed as the Hankel function, which is which we can express, it would be convenient to express as a sum of Bessel J and Bessel Y, Bessel functions of the first kind and second kind. And then we do the same thing. We expand this into the WKB region. Here I already showed the expressions for large L, for L to infinity. And we see that, and we do the same thing that we did in the other one for the WKB. We took the opposite expansion. We expand the WKB for large R, so for R going to infinity. And we see that we can match those ones as well. And there is the fact that the plus solution is matched to the Bessel J, which contains as a prefactor, it contains a factor of L to the minus well. So once again, we have one of the independent WKB solution, we have negligible contribution as L goes to infinity. So we're going to have that the WKB up solution is actually, as L goes to infinity, it can be represented by it's given by only the WKB minus part of the WKB minus independent solution. Then I compared this asymptotic result, these results for as a function of L. I compared it to the solutions that were obtained using the black hole perturbation toolkit for Mathematica. Here I have a plot of the relative error of the in and up solution as a function of L for a particular radius of 6m, and also for I let omega increase with L. We just need to guarantee for this to be valid that that limit condition is satisfied. So it shows a pretty good agreement with the results. So now I will introduce. Those solutions will cover the obtention of the regularization parameters. We'll cover the large L. Now I will briefly discuss the MST method, which is the method that I studied for actually obtaining the solution for not large L. And this is a method that is actually developed for Kerr, but I will apply it for Schwarzschild here. So I've repeated here the Tucholsky equation, and an important fact that I will be using is that the Tucholsky radial equation has this symmetry of L to the minus L minus 1. It satisfies this particular symmetry. So in order to, once again, we want to obtain an in and an up solution to the Tucholsky equation. And the first solution that we're going to obtain is going to be a solution. You're going to obtain it by trying to transform the Tucholsky radial equation into a hypergeometric-like form. So this is the general form of a hypergeometric equation, and we want our equation to look something like this. And we want to seek a solution in series of hypergeometric functions. Since we will not be able to cast the Tucholsky equation exactly into this form, because it has different properties at R equals to infinity than the hypergeometric equation, meaning that our solution will be not valid at infinity, but it will be valid at the horizon where we can enforce the in boundary condition. So we'll construct an in solution first. So we do this particular transformation to the radial function, to the Tucholsky radial function, and we arrive at an equation that looks like the hypergeometric equation on the left side, exactly the hypergeometric equation, and on the right side some other terms which are of other epsilon. A crucial step, the most crucial step for the MST method here is will introduce a free parameter nu that will be tuned in order to obtain a convergent series of hypergeometric function solution. And we will just require that this parameter must be that this parameter goes to L at epsilon goes to 0, so that when we're adding this term, we're not changing the order 0 solution. So this parameter will be called the renormalized angular momentum nu. So then to solve the equation, we just propose an n sets of hypergeometric functions, and doing that using recurrence relation satisfied by these hypergeometric 2f1 functions, we transform the Tchaikovsky radial equation into a recurrence relations, to a three-term recurrence relation for the coefficients of the series. So the non-trivial part is then the obtention of these coefficients. So three-term recurrence relation, they admit a set of two independent solutions, just like second-order differential equations. A sequence solution to the three-term recurrence relation is called minimal, either as n go to infinity, as n go to minus infinity. If we take this sequence, a particular we take the coefficients of this sequence and the coefficient for another linear independent solution, and take the limit L to infinity, the ratio between the coefficients of the minimal solution to any other solution, any other linear independent solution must vanish for n to plus n minus infinity. So the ratio of these coefficients is related to continued fractions, which are transcendental equations involving the coefficients of the recurrence relation. And from the asymptotic behavior of these transcendental equations, one can prove that there exist two independent, there's two solutions, two minimal solutions to the recurrence relations for the coefficients. One that has the property of being minimal as n goes to infinity, and other with the property of being minimal as n goes to minus infinity. In general, these two sequences, they do not agree. So we need to, for example, if we take the sequence that is minimal as n goes to infinity, it will not generally be minimal as n goes to infinity, and we needed them to be minimal everywhere. So we're going to use the freedom of the parameter nu that has been introduced to enforce that this two sequences match. So this one sequence is associated with the so one sequence associated with the left mover function, with the L continued fraction, and the other one with the R continued fraction, and mathematically requiring that they match, meaning solving this equation here, which requires either approximation or numerical methods. And right now we will assume that we can solve this, and we got the minimal coefficients. And this implies, can be shown that taking the minimal coefficients implies that the solutions, the series solution of hypergeometric functions converges. So right now I just give the equation. So our solution will then look like this, where we assume that A is a sequence of minimal coefficients. And it will be useful to use properties of the hypergeometric 2f1 to represent this solution as a combination of two independent solutions to a series of hypergeometric functions. So we just represent it as a combination of two other solutions by using properties of 2f1. And we just rephrase everything in terms of this new variable z hat equals omega r. Okay. The other solution that that we need is a solution that is valid at r to infinity, which will be used to produce an up solution. So I'll go to this part quickly because it's similar to the other one. We do a particular transformation, and we include the parameter nu that will be used to enforce the conversion of the series. So this time we transform the series we transform the equation into something that looks like Coulomb equation and some other epsilon terms on the right hand side. We take a particular ansatz for this this F functions in terms of Coulomb functions. And this particular choice of ansatz makes so this coefficients B of the Coulomb solution are exactly the same as the coefficients A of the hypergeometric solution. Then by assuming again that we managed to get the right coefficients, the minimal coefficients, this is the Coulomb type solution. The solution is a series of Coulomb functions, which are represented in terms of the hypergeometric 1f1, the confluent hypergeometric function here. And another independent solution can be obtained by using that symmetry, L to the minus L minus 1, which corresponds to nu to the minus nu minus 1. So this is not an up solution. To obtain an up solution, we need to do a combination of the two independent solution, and it can be shown that the particular combination that possesses the outgoing at infinity property, purely at good infinity, is this particular combination here. Okay, so the last thing about the MSE method that I need to talk about is the fact that the functions are the solution in terms of hypergeometric function are 0 nu, and the solution in terms of Coulomb functions are C nu. They can be matched in the region where both of them is valid, which excludes infinity and excludes at the horizon. And this is done by expressing all hypergeometric functions in powers in their series representation, and requiring that every z hat term, every z hat power carries the same coefficient. So by doing that, we can represent the in solution also in terms of Coulomb functions. Okay. So now I will use the solutions that I've now I use will obtain the regularization parameters using the large L WKB for this particular case of the circular geodesic. So here I just repeated the definition of the force of the cell force, except that we're doing the L mode of the force, so we have everything is label L here. That's the only difference. So to obtain, we're just going to obtain A alpha and B alpha because those are the minimal, the only ones that we need to obtain in order to obtain something that is a sum over L that is convergent. So we can, what we'll do is it would be convenient to separate our radial modes into symmetric and antisymmetric contributions. And we do that by taking this particular definition here. And we want to calculate the force due into the antisymmetric part and the symmetric part of the Green's function modes. So we define the minus part in the minus part of the L modes of the cell force and the plus part of the L modes of the cell force. And we wish to investigate the L of to infinity behavior asymptotics of these two expressions to find the regularization parameters. So right now I take the specialization to a constant radius, and for a constant radius, the minus Green's function modes vanishes because we have a subtraction of this become identical for r prime equals r, and the derivative survives. And so since the fact that the antisymmetric part of the mode vanishes immediately implies that only the radial components of the cell force modes can be non-vanishing, because every other one will contain this term, every other component, and this does not contain any omega dependency, so we can easily Fourier transform it to obtain some delta function. Okay, so then to obtain the cell force modes due to this antisymmetric part, we just integrated over tau over the world line and evaluated at as z0 at the position of the particle at tau equals 0. And we obtain this expression, which is proportional to capital L. Remember that capital L is L equals 1/2. And this is identified with the AR term in the expression for the modes of the singular cell force. Okay, this was easy because we didn't need to use any actual expression for the radial modes because everything got canceled out. To obtain B alpha, we will actually need to use results for the in and up solutions, homogeneous solutions, and we will do that by assuming as L go to infinity. The in and up solution can be represented by the WKB solutions. We just need to divide it by R to get Tukowski solutions, Tukowski radial functions. And then we can represent the plus part of the modes in terms of those S functions coming from the WKB method. Then we can expand this modes to whatever order we like if we calculate by collecting terms that are in the same order in the WKB series. But for the purpose of P alpha, we just need the leading order terms in the WKB expansion for the green function modes. So see that both of them depend on negative half integer powers of U, and we can actually calculate this integral easily. So we're going to Fourier transform GL omega and its derivative. But we need to be careful with the fact that we cannot actually integrate from minus infinity to infinity because our WKB solutions are not uniform in omega. Recall that they become invalid at that limit omega squared over VL if it is greater than 1. But we'll assume that performing an integration up to omega equals square root of VL is enough. Then to perform the omega integrals, we just use Hankel integrals, and we obtain that the Fourier transform of these functions, radial and time functions that we got from the WKB, they're obtained to be given by some Bessel functions. And lastly, we just need to integrate this over the trajectory, over tau. However, these integrals here that contains the Legendre polynomial and some Bessel functions are not that easy to solve. But if we recall the properties of the singular field, we can actually simplify things a lot. So the singular field, it is the term, it is at the x to the worldwide limit. It becomes supported only at the vicinity of the particle, sourced only at the vicinity of the particle. So we expect that the large L of these functions, of large L of these integrals, is determined by only integrating over a small vicinity about the position of the particle, and just don't need to carry this integral all the way to minus infinity. So we change the integration limits here and integrate it over a region around the particle. And inside this region, we're doing that a symmetric region about tau equals 0. And inside this region, tau is small, and we can expand everything for small tau. But we need to be careful with the fact that we're also doing the large L. So we need to introduce some kind of mode scale analysis here, and we do that by assuming that L times tau equals lambda is finite when producing expansions for large L and for small tau. I will also specialize everything out to the circular geodesic. So then we can using this kind of expansion framework, we can produce expansions for the angular part and for the radial/time part. Due to parity reasons, due to this function being even, we have that only the radial component of the plus self-force modes will survive, because this function will turn odd if we act a derivative of time here, or of phi. And we integrate it over a symmetric interval. So basically, all of these results are in terms of Bessel functions, Bessel J's. And we know how to, and then the self-force modes become given by some integral of products of Bessel functions, which we know how to integrate. And the L dependency appears only at the at the integration limits, because we change variables to that capital lambda. And to take the L of to infinity of this expression, we just take the L of we just sub in the integration limits for infinity, and then we arrive at the expression for BR, which is the same expression that is found everywhere else in the literature. I'm almost running out of time, but going to the last part here, which is the actual calculation. So to perform the calculation of the self-force, I'm going to use the method that was introduced by Hikida 2004 and in collaborators. So in this method, we're going to use that Coulomb MST Coulomb solutions to construct the radial modes of the radial green function modes. And since the in and up solutions are given by a combination of the same two basis functions, some of these have psi thetas will cancel out for some terms, because you have like theta x plus theta minus x, which is 1. So that induces a separation of the modes into two pieces. One piece that contains theta functions, and one piece that does not contain theta functions, contains only combinations of the homogeneous solutions. And that this piece is therefore homogeneous solutions to the field equation. Then the separation of the force modes induced by the separation of the radial Green's function modes. We have that the bare self force is given by a part coming from this R tilde function, R tilde modes, and from the S tilde Green's function modes, radial Green's function modes. And since the R tilde part contains only homogeneous solutions, it produces it is regular. Sorry, I have it wrong here. It is regular from the start. So we do not need to regularize this part. The only part that is singular is the S tilde part. Comparing to the framework that we had before, the Detweiler-Whiting framework, we have that this bare self force is comprised of a regular part, which is the one that we're interested in, a singular part. So since the bare self force does not depend on the particular scheme that we adopted, we can rearrange this equation and write the regular part at this particular combination here, particular equation here. It seems like we complicated things a lot, because we had 2 pieces to calculate and now we have 3. But we can use some properties here to figure out some things. First of all, is that the left-hand side must be regular, so that the right-hand side must be regular as well. And since R tilde is regular, all of the singular terms coming from S tilde must be canceled out by the singular terms coming from the S part. From the perspective of the modes, this implies the S tilde has it has a similar structure. The modes of S tilde have a similar structure than the modes of the FS force, and the terms that are divergent when summed over L, which are the A alpha and B alpha, they must be the same. Exactly the same. And it's only these terms, the D tilde terms, which are higher order terms, they are at most order L squared. They are allowed to be different between S tilde and S decompositions. So I define this remainder part, which is S tilde minus S, the force from S tilde, the modes of the force from S tilde minus the modes of the force due to S, to the S part. It will be given by only the D tilde terms. So we need to calculate, these are the terms that we need to calculate that they actually contribute to the force. Once again, we do that same kind of split into antisymmetric and symmetric parts and to the S tilde part. And it has been shown that for any orbit, that the S tilde minus part, the antisymmetric part of the Green's function modes, will yield that A alpha L, which we want to get rid of. So in order to obtain the D tildes, we just need to take away from S tilde plus the B's. the V alpha regularization parameter. Okay, so almost the end, but so the difficult part of all of this calculation is that the MST solutions are not easily transformed into the time domain, and that the regularization happens at L modes in the time domain. So that's the most difficult part. To perform the omega integration, we're going to PN expand the MST solutions to obtain PN expansion for the Green's function modes. And the most difficult part of that is actually obtaining the coefficients omega, the coefficients alpha, sorry, the coefficients for the MST series. And you can do that by actually expanding the three-term recurrence relation about epsilon equals 0. And one property is that the expansion of the coefficients to the three-term recurrence relation, they are not uniform in N and L. That means that we cannot get a general expression for these coefficients, but the irregular behavior, it appears at L equals minus L minus 1. So from L equals minus L minus 1 up to L equals infinity, we can get expressions. We say that the coefficients are regular behaved because this three-term recurrence relation coefficients have this particular form. And if we use just these regular behaved coefficients, we can produce general expansions for the homogeneous solutions that are shown to be valid. We can write an expansion containing n p-n orders, valid up to n p-n orders for all of the modes that satisfy L is greater than n plus 1, using only the regular coefficients, because the irregular ones appear beyond the p-n or desired p-n order. And a similar statement can be made for the renormalized angular momentum. So here I just show one of these generic expansions. We actually create them by pulling out 2z new factor out, and we expand just this part, and it's given as a simple powers of z and epsilon. Okay. So by using this expansion, we can obtain an expansion for the S tilde Green's function modes, and it has the particular property of not containing any omega term, omega to the new term, which would produce an undesired dependency when that is difficult to integrate over frequency. So it just contains simple powers, polynomial in omega, which is easy to Fourier transform. And also, one can check that the R tilde modes, they are of order V to the 2L minus 1, so that we do not need to compute these modes all the way to infinity. We can just just need to calculate the first n plus 1 modes to obtain an NPN result for the force. So lastly, I decided to take this particular scheme to do the calculation. So I'll calculate one part of the cell force numerically and another part analytically using the PN expansions. For the numerical part, we'll start at L0 and go to a particular value of L, which if we choose this value to be greater than n plus 2, it is useful because when we calculate the PN part, the PN part will not contain R tilde because the R tilde part will be too high of a PN order. We are already past this n plus 1 L modes. So we calculate the first n plus 2 modes numerically, and then we can calculate the first the other modes from a PN expansion.
Alexandre, just one question.
That's 3.
Alexandre, how many slides have you got?
I think I had like 2 or 3.
Okay, it's just time to start finishing up.
Yeah. Okay. So I'll finish up. I'll wrap up right now. So since the GS tilde has a simple dependence on omega, we can easily integrate it to generate some delta functions, and then we can obtain expansions for for the FS to the L modes. And then we take to obtain an expansion for the BR parameter with that we need to take out from this expression. We can obtain already from here by taking the L of infinity of this expansion and subtracting it to arrive at the contribution of this S to the minus S part that we wanted, the modes. These are easily summed over L using, you can just plug that into Mathematica, and it's solved using partial fractions, I think, something like that. And here I just, so lastly, these are my results that I obtained. I use different values for the L0, which is the value of L on which I stopped using numerical and start using the PNs. And as expected, the larger the radius is, the results are better, and the larger, by just increasing a little bit, the L0. So I forgot to say that these are results obtained from 8 PN expansions, and so the minimum that we can start from my method is 10, L0 equals 10, and just by increasing a little bit to 15, we can, or to 20, we can improve a lot the relative error for the 6M, which is the innermost stable circular orbit. And for a larger radio, that does not actually matter a lot. And the value I'm comparing to is a value that is taken from the literature, obtained by calculating numerically the first 50 L modes and fitting for the other L modes of the sun. That's it. Thank you.
Thank you very much, Alexandre. So we're moving on to the questioning phase from the examiners. So I'm very heartily thankful to the two examiners that we have here. So there is Barry Wardell from University College Dublin in Ireland, and Sergio Jerez from the Federal University of Rio de Janeiro in Brazil. We'll start, even though it is an online talk presentation and defense, we're usually starting with the furthest person, which is Barry Wardell from Ireland. So Barry, feel free to start the questioning whenever you wish.
Great, thanks very much. Hopefully you can hear me talking now. Thanks very much for the nice presentation and the interesting read and the dissertation as well. I guess I have a few questions. You presented these two approaches to solving the radial equation, this WKB method and the MST method, and you showed a plot, I think it was slide perhaps 34, where you showed that at large L they agreed quite well, and then it looked like they disagreed not well. They agreed not quite as well at low L. Can you be more quantitative about that comparison? So do you have a plot?
Sorry, which number? Which slide?
So this plot here, yes, this one. Sorry,
Yes,
33. I was off by one. So this comparison suggests that the two methods agree quite well. Is that how I understand this? This is the relative error compared to the toolkit and the two solutions.
Yes.
Which increases at low L. Can you be more quantitative about exactly how that difference should scale with L, for example? Or can you decrease the difference by going to a higher order in your WKB expansion? Or how would you improve this relative error?
So this plot here, I've included the first three of those S functions of the WKB series. So if I include, I think I have not plotted it by including more functions, but that will probably scale down the error even faster. But I have not.
Do you know have any analytic kind of expectation of how it would scale, how rapidly it would decrease as you add terms to the series, or perhaps how rapidly the error falls off if you increase L?
No, I have not done that.
Okay, that's okay. And in terms of the You're not necessarily suggesting the WKB method as a method for obtaining solutions, are you? It's more that it's more useful in chapter 5, where you actually use it for doing the large L regularization. Is that correct? Or do you think this is actually a useful method for also obtaining numerical solutions for the retarded field?
No, I think I introduced it to obtain the regularization parameters. So I think it might be useful to obtain higher order regularization parameters, especially for the circular orbit. For the circular for actually any fixed radar orbit, because there's lots of simplifications, and these functions that do not have so the odd functions, which are more simple, just these functions that appear for the circle for when calculating the self-worth modes for the circular orbit. So you might I tried, but I have not managed to actually obtain the higher order regularization parameters, but that might be possible.
Okay. Good. And these are at a specific R value, R the 6, is that right? Do they also have a dependence on where you evaluate them also affect the accuracy, or is it fairly uniform in R?
Yeah, so the key thing is that because we're not plotting actually L to infinity, if we let if we decrease R, we're decreasing this the value of this potential, so that this condition is getting closer and closer to not being satisfied. So you'd have to plot to a larger value of L in order to have a relative error that is smaller, because you're getting closer and closer to the limit where the WKB breaks.
Okay, but I guess this is already a fairly small R, so.
Yeah, I plot like the worst case scenario here.
Yeah. Okay, great. Great. I guess a sort of related question is, so you're proposing to use this WKB regularization method. Do you know that, does this recover the Detweiler-Whiting regular field at the end? Is that something that you can show from the method? So I think in the thesis you had this nice description of the Detweiler-Whiting split of the regular field defined in terms of a regular green function. Can you show that this WKB subtraction approach yields that?
Okay, so I think because I was running out of time at the end, I think I was not clear about that, but I showed that the B alpha parameter obtained from the solution matches the B alpha from the literature. So that means that using the WKB, I'm getting the same regularization parameters that people are getting by taking like local expansions of the singular field, which is the default way of doing it. So what remains open is that is to see if my higher order terms from the WKB, they are the same as the one that you would obtain normally from the singular field, that Weiler field, and then we would of course obtain the same regular field.
Okay, great. So I think you did at some point show the BR parameter. It looked similar to, I don't know what it looks like off by heart to know for sure that's the same, but it looks similar, all right. Although you've given it in terms of these hypergeometric functions, I guess these can be written in terms of elliptic integrals, which is kind of a way that these regularization parameters are often written. Do you know if that's the case?
Yeah.
These 2f1 functions.
Yeah.
Yeah. So you think they do reduce to elliptic? They are just elliptic integrals for these the arguments given here.
Yeah, it's just because the referencing that was trying to reproduce the referencing that was getting for the literature was in terms of these hypergeometric functions, and then I just left it like that.
Okay. And what do you think would be the challenge then? You said you haven't gone to the next order yet. What would be the biggest challenge in trying to push this calculation to higher orders?
Okay, so the biggest challenge, the next order terms, they increased for every order term the calculation that I try to go to next order term. You will have, so let me go to the 4 because it's useful. So at leading order here, I have used we have basically 3 powers of u here that we need to integrate over omega, and then afterwards integrate over the trajectory. At the next order, I think I had like 6 or 7, something like that. So it's just like a tedious calculation. I was trying to implement that in Mathematica, by Mathematica does not do any of these integrals automatic, so I had to add them as rules, substitution rules. And yeah, I think it just a lengthy calculation, but I think it is feasible.
Okay, great, thanks. I guess I could next maybe ask a more general question, which is, everything you presented here has been for the Schwarzschild case. How much of this do you think you could carry over to study, for example, Kerr, solutions of Kerr spacetime? What would carry over, or what do you expect might not carry over? And are there kind of fundamental challenges that you anticipate?
I have not tried applying this WKB method for Kerr. I don't know what it would look like. What it would look like, because when studying for when I got to masters, I specialized just Schwarzschild very early on, because I had actually no experience with working in black hole physics. So I'm not sure how because Tchaikovsky equation, the things that are presented that are just basis things that I studied from the literature, they of course translate, right? The chapter 2, the Detweiler field, all of that, MST, all of that is already in Kerr. I just have it specialized here. But the particular thing that I work that is different, which is the WKB derivation. I don't know. I'm not sure how would that translate to Kerr, because I actually do. I would have to actually change the equation, because I'm working with the Regge-Wheeler equation. So I would either try to apply the same thing to the Tchaikovsky equation, or I would need to later transform the Regge-Wheeler solutions to Kerr solutions to Tchaikovsky solutions in Kerr, which is not just dividing by R as in this case. So I'm not sure.
Okay, yeah. So I guess you feel the 2 places you're suggesting are, one, that you have to figure out how to use Tchaikovsky instead of Regge-Wheeler, and 2, that you're not, I guess it would need to be investigated whether the WKB approach can be applied in the Kerr case, or how it might be applied. Is that not fair? Summary of what you've said there?
Sorry?
Just so I understand, is that you're suggesting the main 2 things are, 1 is working with Tchaikovsky instead of Regge-Wheeler, and 2 is that the WKB method may have some things that are specialized to the Schwarzschild case?
Yeah, I don't know. Yeah, I mean, I used it already at the Schwarzschild. I have not tried using to use it for Kerr. I would need to try to apply to the Tchaikovsky equation, which I have not tried. But yeah, I'm not sure. I just have not had the time to try.
I guess maybe we'll have one last question, if that's okay. Different type of generalization. You've looked at circular orbits. Do you think the method would be applicable to other types of orbits in just, for example, limited to Schwarzschild spacetime now, let's say eccentric orbits or even unbound orbits? Have you looked at that at all?
So I think there are two things which they are key to answering that question. First is one that I'm coincidentally at the right slide right now, is the fact that the WKB solutions they are not uniformly valid in omega. Something that I have omitted here, but I talk about in the thesis, is the reason why taking this restricted integral here in omega works, gives the right regularization parameter. And this is because for a circular geodesic, say, you have a top frequency that contributes to the self force, and that frequency is contained inside this region. I have not, so you would have to check whether this is satisfied for any other particular orbit. Also, the one thing that made the calculations very much more easy is the fact that I took that when taking, so as I said, when you take R to be R equals R0, these modes here, all of those even functions that have complicated integrals, which I give one of them in the thesis, in an appendix which have complicated elliptical function dependencies, they would appear. And I think the right way of doing that would be changing all of this, instead of doing like, I mean, taking, first specifying, starting. So I think the way you could get rid of those complicated integrals that appear for cases that are not circular, so that you have the even S functions, is by doing large L asymptotics before. So at some point before you get those complicated WKB elliptic integrals, and do the large L of that at some stage before, not actually at the end, as I'm doing here.
Okay. Good. Thanks for the answer. That was very enlightening. I think that's covered everything I have here, so maybe I'll pass back to Mark and see if anyone else has questions.
Thank you very much, Barry, for your comments and questions as an expert, world expert in the field. Just a quick comment on one of your questions. This cannot, at least it would be very surprising if it reproduced to the Weiler-Whiting-Grimm function, because there's no, we don't even know what the boundary conditions that satisfies at, we just haven't put that in here at all. It reproduces the local behavior, but not, at some stage it will stop being that Weiler-Whiting, most likely.
Okay, yeah, thanks.
Thanks, Barry. Okay, so now we move on to the more local examiner, Sergio Geras from UFRJ. Sergio, thank you very much as well for your participation in the defense. Feel free to start whenever you wish.
Sure. Thanks, Mark, and thanks, Alexandre, for the invitation. I really enjoyed reading this thesis. I've known Alexandre since undergrad, but he's come a long way. It's really nice to read that thesis. It was really well written. So I have a few points here and there, but I'll just leave that for later, because I'll just send you the PDF with some annotations, but they're really localized questions that I think they could be improved. Some little things like you promised us a Mathematica file with some notes, but I didn't receive that Mathematica file, but I think it's on its way. So things like that, I don't think it's worth mentioning every now and then. But I do have some questions more on the physical interpretation of your results. I understand that you've done lots and lots of calculation. You exceeded expectations, but I do have some questions. For instance, we'll have a sum of modes, L, right? So what does that physically mean when you cut off, when you start when you cut off your sum in L's? So what are you missing when you do that? If you don't use so many L's as you can, because it's a summation, right? You have to stop at some point. So physically, what does it mean to stop at a given L? If you stop at a too low L, what are you missing then? But L introduces a scale, right? But so you're missing information, pieces of information on larger scales or smaller scales. What does a large L point to?
Well, I would assume that well, since the so let me go back to so I would assume that we're no, yeah, I'm not sure. I haven't thought about that.
Well, okay, but so let me ask you some related question. So you have written an epsilon parameter which is equal to omega times the Schwarzschild radius. Is that right? Omega times RS, right? So what does that tell you about the omegas that you are assuming? So epsilon you're assuming to be small, right?
Yeah.
So because you neglect all those pixels that are on the right hand side of rotation, which are of order epsilon square. Is that right? Did I get it right?
Yeah. So
I didn't get the number of the page.
Yeah.
Yes. Yeah. That's it. Yeah. So you have this epsilon. This. Yes. Go ahead.
So the MST solution here it excels for small epsilon. You're right. Because this perturbation to the hypergeometric solution would be small. But it is not actually a series in epsilon. The sets that we have, we just I mean, we plug in the insets and identify that the the convergence, the series would converge as expected for as for smaller epsilon it would converge better.
Okay, yeah, I understand it's not a series in epsilon. I'm just saying that you are neglecting higher order terms in epsilon, right? It's not a summation or anything like that. You're just assuming that those terms are small, right?
Yeah. When I do, I do that when I do the PN expansion.
Yes, yes. So physically, what does it mean to have a small epsilon? What you are assuming about your system? Is a larger mass black hole? Is a smaller scale? Or what? So if you look at your definition of epsilon. Yes.
Basically, epsilon. I'm explaining for small epsilon over z, which is m over r, which basically means that an expansion for a weak field, right?
So they're looking at the larger spatial scales, right?
Yeah.
Because you are looking at radial coordinate, which is much larger than the Schwarzschild radius. And if you look at the previous expression, what I have written here, that epsilon was equal to omega times times the shortest radius, 2m omega. And so that would mean that you are also would be looking at smaller frequencies, right?
Yeah.
So I was just wondering, I myself don't have a final answer for that. So I was just wondering, what does it tell you about your system? You're assuming a small frequency, so your system cannot be too close to the coalescence, or physically, what is the setup that you have to assume in order for these terms or the epsilon to be actually negligible? Physically, I was you see my questioning.
So
I understand that I was going to say that I understand that epsilon is small and you're neglecting the mathematics is just fine. I was just wondering what would that correspond to in the real world. It looks should I have two black holes close to each other, or they're far away, or what's the physical setup?
Okay. So we're basically expanding our order zero would be for this PN expansion would be like a Keplerian Newtonian physics, because as you see here, we're taking z hat, which is omega r, to be capital omega. Capital omega is the angular frequency for circular orbits. It's actually the angular velocity, the angular Keplerian velocity, as in Newtonian physics. So we're basically saying that we are at low velocities. And that we are close to classical physics orbits.
Okay. Yeah, that's what that was my feeling as well. So the second question I have is about the mathematical toolkit that you mentioned a couple of times. So I was wondering, for me, it looks like a black box. So I wonder what was the method that they use. It's just a full numerical, full brute force calculation, but even if it's fully numerical, there are some issues on the method to solve to numerically solve a couple system of equations, right? So it's not just a done deal. So what can you tell us about these toolkits?
Yeah. So I've put that on the thesis, but I did not mention here on the slide. So I used, even for comparing the large L when I give this plot here, I use the MST method contained in the toolkit. So just basically the MST series halted at some given after some given precision has been obtained. I tried also comparing to full numerical results, but the result for the toolkit were kind of breaking for when you get to such large L. It was taking like hours to run one L mode. So I managed to do only with the MS, comparing to the MST. The MST solutions given by the toolkit.
Did you mention that in your thesis, that the numerical results from the toolkits didn't work out?
No, I just mentioned that I used the MST ones.
Because I think you should, right? It's something in your favor that works in your favor, right? Because the full numerical calculation does not quite work, then it's another reason to use something else.
Yeah,
right.
Yeah, it's not that they don't work; it's that they are kind of expensive to run. They take a lot of time.
Yeah, but I mean, you actually tried to use that, right? And so we should say that they are not here, and that's the reason. Right? So I have just a couple of more questions. So when you're talking about the WKB approximation, so it reminded me a paper of mine a couple of years ago about the scattering calculations on a black hole, from a black hole. So there's something, did you use that? Did you look this up? I mean, try to use this approach to study scattering from black holes, and even just to take advantage of a previous question about the expanding that calculation to Kerr. if you manage to actually make this expansion, you can use this approach to study superradiance around the third black hole. And I do know that double Quebec approximation is valid because you just have to change the frequency there. It's going to be the frequency of your plane wave expansion is going to be the frequency minus the frequency of the black hole itself. So if you have a different sign, if your frequency of the incoming wave is smaller than the frequency of the black hole, then it looks like a negative effective frequency. So it looks like this wave will be coming out from the black hole instead of going in. So that could be superradiance, which is something that is really nice to study. So if you manage to expand your calculations there, it doesn't have anything to do with cell force. That it's a different problem, but with the same approximation that we used. So my question is that just besides suggesting that you actually look into that, my question is just, have you looked into scattering around Schwarzschild black holes using that approach, the WKB approach?
No, I have not.
Okay, so let me just give you this suggestion. We can talk about it later if you wish to.
Sure, sure. You can email me about that.
Sure. And the last question is about the cell force itself. So we defined it nicely in the very beginning of your thesis. But what I missed is, again, the physical interpretation of the calculation. So we've done, we spent 2 years making a calculation, beautiful calculation, really nice results, etc. But I missed the physical interpretation. So the cell force, where does it point to? What should it do to the particle itself, right? Does it slow it down? Does it speed it up? Or does it point inwards, outwards? So what you explained it correctly, right? It's just a correction due to the geodesics because it doesn't actually follow that geodesics because the metric's not actually the zeroth order metric, right? So that's a correction on that geodesics. So, but in the real world, what does happen to the particle when it's subject to this cell force? Where does this cell force point to?
For this case here, I just have a R component which will cause the spiral, so it points inwards. But in general, you can have conservative and non-conservative parts of the cell force that may drive the particle into the spiral and may also slow it down, point like in the direction of, if you're saying elliptical orbit, you can also have a non-conservative part of the cell force that may point in the decelerate the particle.
Yeah, because, yes, that's my point exactly. But it should slow the particle down, right? Because there should be emission of scalar waves in your case, right?
Yeah.
So the system should lose energy. So and at the same time, it should move inwards because it's losing energy. So the orbital radius should decrease, right? So I think that did you mention that? Because I think I missed if you did. If you did mention that.
No, I think I didn't.
Yeah, I think that you should just mention that, right? It's just it's pointing that there is a lack of energy conservation because that's exactly. So I think it's interesting not just because it's the physical interpretation of your calculation, right? At the end of the day, there is some physical prediction that you have to compare to. But besides, you can also say that, oh no, this emission of scalar waves cannot be calculated up to this order. You have to go to a higher order in some parameters in order to calculate that missing energy, for instance, right? So it's something that is not clear for me if you stop at first order or you have to go to higher orders in order to have these effects present in our calculation. So I think it's something that you should mention, right? This energy loss and the pointing of this effective force, right? It points towards in this direction, but it slows down also. So I think it's something that we can relate to, right? Physically, what happens to that test particle. Let me just go through quickly my notes to see if there's something that I missed. But I think I mentioned everything that to. Oh, actually, there was something that, yes. So in your thesis, page 16, page 22 of the PDF file, you mentioned the von Black biscalar. It's just out of curiosity. Do you have a thesis on you, or can I just quote?
I'm opening the thesis right now.
Oh, okay. No, it's okay. Take your time. It's just a curiosity because I think it's the same thing that I read about in a totally different context. But I wonder if it's the same thing. Maybe you have heard it also in a different context. It's about the von Black biscalar.
What was the page again?
It's the page 16 of the thesis, the page 22 of the PDF. It's near equation 2.27. So if you look for equation 2.27,
Okay.
you'll find it. Here's the sentence right below equation 2.27.
Can see it.
Right.
So
So you
what-
mentioned that this delta is the von Black biscalar, which is related to the focusing of divergence or divergence of the geodesics in the background spacetime. And so I've heard about the von Black determinant, which is actually related to the focusing of trajectories. If when they're calculating a path integral, and this von Black determinant shows up, but when you have the convergence of many paths, given an initial point and a final point, that is not enough to define the trajectory that your part will follow, because there is a convergence of all the trajectories that start here. They will all end up here, just like an harmonic oscillator, for instance. They will have always periodic solution. They all have the same frequency, regardless of the initial conditions. So cases such as this one, there is this parameter, this actually the determinant that shows up in that path integral. That is the von Black determinant. That will go to zero, and it's in the denominator of your expression when you're calculating probability of that path. And then it diverges, the expression diverges because it's related to this focusing of trajectories. So I was just wondering if you have seen this von Black biscalar in a different context, such as this one that I briefly explained.
Yeah. It seems like besides being different, it seems like it's a quantity quantifying similar things, right? Because you're very interested in the focusing and the focusing of the geodesics that goes from the source point to the field point, and that will be related to the curvature. But I mean, I just included this discussion here just to say that the expansion for this U biscalar is known, and it is a known quantity that as you said, appears in other contexts, which is the von Black determinant, which is related to the von Black biscalar. Yeah, but
it's okay. It was just a matter of curiosity. I was just wondering if you have heard about it in a different context.
no, the first
actually. It's okay. Later on, I can throw you a particular reference that talks about it, because I think it's exactly the same thing, just in a different context. So it's okay. Okay, so I'm all right, Mark.
Yeah, thank you very much, Sergio, for your kind contributions and questions. Just a couple of quick things. Well, one about the Van Black. So that's in the seasons, right? it's introduced below equation 227 in the thesis. So it's the, it's the coefficient in the direct part of the Hadamard form for the Guettard function, which also appears in the Weiler-White-Green function. Also, just a quick comment on both yourself and Barry. I did ask about care, obviously, because that's that ultimately that's the holy grail for any black hole calculations. It is much trickier. It's not just a incremental difficulty in the calculation. It is significantly more difficult to do it in care for many reasons. The spheroidal harmonics, so the angular part depending on the frequencies and also depending on m. So here there's spherical symmetry. You can do the sum over m analytically to get Alexandre's polynomial, but you've got an L and M dependence, an omega dependence appearing the spheroidal harmonics in Kerr. And I know even just getting the large L asymptotics of the spheroidals is quite tricky. And I think it depends on whether the relationship between L and M and omega. So it's not, it gets quite tricky in the whole region of parameter space. Okay. Well, again, thank you very much to both yourself and to Barry for all your contributions, and to Alexandre for the presentation, well, I'm aware he's worked really hard, and he's done amazing progress and work doing all these calculations all throughout the master. So I know that your understanding of the cell force and all the different methods has increased hugely, and to this high level that you've shown today in the presentation and in the thesis. So I'm delighted that you got to hear. So now I think it's going to be time for the two examiners to decide on what to do. Larissa. So I think the way it should work is that the two of you have a separate discussion. Larissa, pode me ouvir?
I don't think she can hear you.
No,
Maybe
but
she's away from the computer.
Larissa?
Oi.
Finalizou já a parte das perguntas e da apresentação. Agora, qual
Eu
é o
vou
seguinte?
passar vocês para uma. A gente vai esperar o outro professor?
Sim, enviou um e-mail para ela.
Passo você, o Sérgio e o Barry para uma sala simultânea para poder deliberar.
Eu vou também para a sala, então.
Isso. Eu só tenho que aguardar mesmo o Barry entrar, se ele for participar da deliberação.
Eu posso enviar um e-mail para ela. Acho que é possível
Oi?
que ele tente voltar agora, mas ainda não sei com certeza.
Eu posso passar vocês para a sala e quando ele voltar, eu vou ter que retirar vocês da sala para poder incluir ele.
Ok, tá bom.
Que aí vocês, Sérgio, fica conversando lá na sala simultânea. Aí eu boto outra tela aqui para o YouTube não ficar aguardando muito. E aí, assim que ele entrar, eu retiro vocês da sala e incluo ele novamente.
Ok, tá bom.
Bom,
Obrigado.
é só aceitar na tela de
Aceitar. Larissa?
Sim.
Ok. Estamos os três no break na outra sala, mas o que devemos fazer agora?
Sim, é só deliberar para poder saber se o aluno está aprovado ou reprovado.
Ok, não tem nota, só aprovado ou reprovado, certo?
Isso, não tem nota. Aí é
Não,
só você.
não tem que assinar num documento?
Sim, a ata depois, que eu envio por e-mail, depois que finalizar a defesa.
Ok, ok. Ok, vou voltar
Aí
para o.
eu vou ingressar você lá de novo. Mas
Ok,
assim que vocês terminarem lá, é só sair daquela sala lá que vocês retornam para cá, tá bom?
ok.
Só um minutinho. Mark, como você saiu, eu vou ter que fechar a sala e eles voltarem para eu abrir outra. Que eu não tô conseguindo mais ingressar você lá.
Pode comunicar isso para elas ou não?
Eu vou fechar a sala aqui, aí tem que esperar só um minutinho para eles voltarem normal, porque eles vão ter que sair de lá de qualquer forma. E aí eu vou botar vocês de novo na sala.
Ok.
And Mark, I think Larissa closed the break room.
Yeah, she told me. So you love Barry now.
No,
Okay.
no,
Okay, so what happens is,
yes.
few of us, I think she's going to put us to the breakout room. All you have to do is decide whether whether Alexander passed or failed. But wait until we get back into the breakout room. Agora a Laísa vai fazer uma nova sala, certo?
Okay,
Sim, tá vendo agora? Apareceu na tela de vocês?
yes.
So Barry, get
Apareceu.
in the breakout room if you can. The join button. Okay, so I think. Então, Larissa, agora.
Oi. Agora é só vocês falarem, o Mark falar o resultado da defesa, se foi aprovado ou reprovado,
Certo.
e encerra a defesa.
Okay, obrigado. So, yeah, so I'm delighted to say that it's a definite pass. So there's no grade here apparently in CBPF. So it's either fail or pass, and it's definitely, without any doubts, a pass. So many congratulations, Alexandre, for a clear, definite pass.
So thank you, Mark. Thank you, Sergio, Barry as well. Thank you also. I have not had the opportunity to also thank for the great questions and suggestions that you gave. Also thank Mark. Obrigado, Larissa. Também te mandei muitos e-mails, te perturbei muito nesses últimos dias. So thank you, everyone. And yeah, that's it.
Parabéns, Alexandre.
Alexandre, just send me an email because I don't think I have a current email, so I can send you my annotated version. Right?
Okay.
Yeah, so I think Barry has got some corrections also, suggestions for corrections that he'll email to you or to me or maybe to both of us. And I made, as you were giving the presentation and throughout the questions, I made some suggestions in the overleaf that we share. So I think you'll be able to read those comments there, suggestions for improvement. But there's nothing major. There's no just suggestions for clarification and so on.
Yeah. So I already I told Mark, but I already begun tackling some of the some corrections that I know will happen because some typos, some equations that are inconsistent. And when I first sent the thesis, I don't know if that first version came to Barry and to Jorais, and then I think you got the second version already. But even the second version has some typos, some inconsistencies, and I apologize for that because this last part of my master's, which I had not my scholarship ended, and I having to like work like 6-7 hours in the morning and do the thesis afterwards. So it's been really rough for me. So that's why I think Mark, of course, is the one who suffered the most from this typos and all like silly mistakes. But I thank you a lot, Mark, for surviving this period with me. And that's it.
It's not suffering. I have enjoyed all your interesting work. People are wondering, what have you thought what you're going to do next, or?
So I'm quite not sure yet. I did in undergrad I did cosmology, and then now master's I did black hole perturbation. So I already changed once of kind of same general area, same like general relativity and that kind of stuff, but kind of a different topic. And I'm taking like the rest of this year just to think about, read stuff, and really think about what I'm going to do next as a PhD.
That sounds wise. Fair enough. Okay, I don't want to keep. I know that.
Just let me know if you want like to talk about something, because I think you have really great tools to work to bring up more and more results, not only in that black hole, but in a lot of physics that would in your future. So let me know if you want to talk about it.
Okay, thank you, Sergio. I will get to you.
So I think there should be some paperwork, right, that you have to sign.
Yeah. Larissa?
Desculpe. Tem alguma documentação, Larissa, eu acho que a gente tem que assinar, né?
Tem a folha de rosto, eu vou mandar por e-mail tudo explicadinho. Aí você pode botar a assinatura eletrônica do Gov, se achar melhor. Tá bom?
Tá. Especifica a ordem para alguém mandar para alguém, e depois mandar para a gente assinar o mesmo documento.
Eu sempre peço para me enviar para me enviar para poder enviar para o próximo. Se vocês preferirem que eu bote um e-mail para todo mundo e aí e assim enviando, aí fica mais fácil. Eu acho que fica mais fácil para vocês, não sei.
Quem tem que assinar isso? O Sérgio?
É,
O Bar-
isso, o Sérgio, o Bel e você.
Ok. Você pode enviar um e-mail para os três, para nós três.
Tá.
Mas é que tem que passar para um primeiro, para outro passar para o outro, para depois passar para o terceiro, porque senão cada um assina um papel diferente.
É
yeah.
Então
isso.
tem que só escolher uma ordem. Então, pode...
É,
Yeah. So Barry, so
eu vou mandar para o Barry primeiro, por ser mais distante.
yeah,
Aí eu passo para o Sérgio e depois para o Mark.
certo.
Tá bom?
So Barry, so Larissa will send you an email with a document that you just have to sign. You can do a electronic signature or whatever. Email it back, and then I'll sign it. Well, Sergio and I will sign it.
Okay, yep, that sounds good.
Yeah. Okay, so well, many congratulations again to Alexandre. Many thanks to both Barry and Sergio for all your contributions and for accommodating for the times which I know has been very tricky. E muito obrigado, Larissa,
My pleasure.
Nada, eu que agradeço.
Obrigado, Larissa. Parabéns, Alexandre. Nice to meet you, Barry. Mark, a pleasure as usual. Bye-bye.
Nice to meet you, and congratulations to Alexandre.
Thank you. Obrigado. Bye.
Goodbye.
Bye-bye.
Thank you.
Bye, bye.
Okay. Você também, então.